Welcome back to ECE 320A. Homework number 5 is due tonight. Oh, yeah, you haven't started. Well, you have a few hours. Hopefully you've started and you're just teasing me. But homework 5 is due tonight, and homeworks 3 and 4 were also due prior to exam number 2. We'll talk a little bit about that, obviously that content or those topics in the review session for exam number 2, which is right after this class. That will start at 5. If you can't make it, it will be recorded if you want to watch it at your leisure. But you probably want to look at it, notes and or video, prior to exam number 2, which is the next time we see each other in this class at this time. Exam number 2 is Thursday at this time, which is 3:30. One announcement in terms of activity: tomorrow, Wednesday at 4 p.m., there will be a technical elective and AMP info session in room 530 if you're interested in attending. That's at 4 o'clock. The plan is to record that and make it available to you. So you shouldn't, if you have a class or a conflict, hopefully you'll be able to watch that if that's what you would like to do. Course material that we haven't covered in class, but hopefully you've made available to you for homework assignment number 5, and that deals with poles and zeros, which we've talked about. We had the tense on them all, so I know we've talked about poles and zeros, but there it's formally presented. Final value theorem and initial value theorem is now available also, and those are not each 75-minute videos if you're watching those. Those are compressed pieces of content, but it's parceled out into 3 little sections of poles and zeros, final value theorem, and initial value theorem, and we will look and see how many of you have actually done any of that with our quiz to begin this class. But just to make you aware, I'm not sure how many of you will want to be at office hours. Don't come next week on Monday or Tuesday. I won't be available, and I will try to be here Tuesday, a week from today, in class. So that's the schedule. I'm basically telling myself if it doesn't mean anything to you. Goals, we'll talk about the process for exam number 2. We'll have, and this is for today's class, we'll have a quiz on the final value theorem. We'll look at some examples of applying the initial value theorem. I'm assuming you now have that material understood as far as when it can be applied and how to use it. We'll talk about complex poles with real numbers. I think that's also been made available as a unit or a piece in D2L. But I want you to be very comfortable with this equivalence between writing sines and cosines that are at the same frequency as either a single cosine expression or a single sine expression. And in this class, we're going to focus on writing that as a single cosine expression. And that sine and cosine at the same frequency could be exponentially damped, or it doesn't have to be. But if it is exponentially damped, the exponential damping needs to be the same if you're trying to combine those sines and cosines of the same frequency. You could have all sorts of things going on. You could have exponential damping of 2 types with sines and cosines, and you wouldn't be able to combine those. And then we'll look at a circuit example, and I think that might get us into a transfer function. If you're interested in transfer functions, we'll look at that. The process for exam number 2. You now get 2 sheets of notes that you can bring in, and that's front and back of those 2 sheets, but you should make sure that you incorporate the Laplace transform tables or the information in the Laplace transform tables, however you want to write those. And I'm saying tables because you have the transform pairs in table 12.1, and you also have Laplace transform operations or theorems. How do you use modifications of these Laplace transform or these Laplace transform properties to possibly derive or obtain Laplace transforms that aren't an exact match to the table entries of those pairs. You can bring a calculator, something to write with, and we'll try to sit in alternate rows again, or columns again, and that will be then to prevent you from talking to your neighbor, which isn't here, but you can't bring a computer or your cell phone, no textbook and no class notes. And that shouldn't be a surprise. Yes? TI-89 and TI Inspires, that's what I'm assuming is a graphing calculator. They are allowed. Do you not want me to allow them? No. If you have them, you might as well use them so that you can convince your parents it was a good investment, if that's the case. If you don't have them, I don't think it's going to be any negative impact on you. You need to be able to work these on your own without necessarily having the calculator do some things for you. Let's now look at this final value theorem quiz. And these are different pieces, A through F, maybe with multiple A's and B's occasionally. And I want to now have you answer a yes or no, and I'll do this by polling the class. Everybody brought your clicker, right? Oh, I don't have a way of monitoring a clicker, but I do have a way of monitoring your thumb. If you now want to say yes, that's a thumbs up, and if you want to say no, that's a thumbs down. But I don't want your answer immediately. I want the answer at the count of 3. And you need to hold it here so that your neighbors don't see what your answer is. Because then they'll go, they'll look and copy. Okay? Just be honest with your answer. If you don't know, I guess you could hold it level. Maybe. All right, so number A. Can we apply the final value theorem to this transform? And I need to count to 3 before you show me your thumb. 1, 2, 3. Pardon? You guys are having too much fun, aren't you? Spring break was 2 weeks ago, wasn't it? I don't know. I can't. Obviously, I didn't get one. So that's yes. And why is it yes? So what's the stipulation for applying the final value theorem? Okay, the answer was if you solve for the denominator and set each of those factors equal to 0, they will end up being negative, real parts. They're in the left half of the complex S-plane, those S values that cause the denominator to vanish. In the book, it will say the poles of S, capital X of S, are all on the left hand side of the S-plane, or you have 1 at the origin. Okay? Actually, no. All of the poles have to be on the left half plane, not on the imaginary axis. Okay? So, I gave you a way, I guess, how to figure this. What's B? Yes or no. And now I want the answer in 1, 2, 3. This one's causing some issues. This one actually is yes. So you can apply the final value theorem to this. And it looked like we had some disconnect. And if you now did this, you could, if you wanted to, apply your inverse Laplace transform to this. This is pretty easy. This is A over S plus B over s plus 1 and solve for a and b. Or you can say, okay, what's this look like as t goes to infinity? This would be a plus b e to the minus t. And what happens as t goes to infinity? You're stuck at a, right? Or you're going to a, and that's a bounded value, so you can apply the final value. What you're looking at is s times x sub b of s, and you want no poles of s, capital X sub b of s, in the right half plane. You want all of your poles in the left half plane. So you're looking at s, x sub b of s, checking the poles of that. In this case, that s cancels that one s in the denominator, and you're okay. So you can apply the final value theorem to that. Okay, x sub b prime with a 1, 2, 3. Thumbs. You came in maybe. So the no is a thumb down, the yes is a thumb up. What are we saying? Mostly down. This one is no for the exact reason that I tried to describe before. If you now look at the poles of s, capital X sub b prime, you'll still have a pole, one pole at the origin. That's what happens if you inverse Laplace transform that. You're going to have a constant plus something that goes up with time t, and then you'll have a decaying exponential. As t goes to infinity, that thing that's going off at t is going unbounded. That doesn't have a final value, and the final value theorem cannot be applied. C. So b prime was a slight variation on b, is why I labeled it as b prime. Don't answer yet. So now 1, 2, 3. And why are your thumbs down, or why are you saying no? If this is the S-plane, you now have poles right on the imaginary axis. So if you're looking at this circus tent and you're walking up the imaginary axis, you're going to run into a pole, and that's going to go off to infinity. In this case, these poles mean that that particular, if you inverse Laplace transform, you're going to have a cosine, or in this case, it's actually a sine, at what frequency? What's the frequency of the sinusoid? Is it 5? Is it 2? Is it 1? Is it 7? What's the frequency? It's the square root of 1, isn't it? And it's 1. So the oscillate, and that's where the pole is. The pole is at 1 radian per second. That gives you how it's going to shake as a function of time, is 1 radian per second. And because it's going like this forever, it never has a final value. It's bounded. It's a bounded answer, but it never hits a final value because it just keeps going up and down, up and down. D. What was the amplitude of that sine wave in the previous? 5. So it was 5. So it's going up and down quite large. If you D, getting back to D. 1, 2, 3. I have some no answers in the back, huh? By Thursday, you'll definitely want to be able to indicate your thumb response on your paper. So it should be a yes Was there a question?
Yeah, so the last part in C, it's no because it was exclusively on the J plane, or is it? It can't be like. Could it be like to the left but up?
The question was, where are these poles located on C? Right now they're on the imaginary axis. Is it critical that they're on the imaginary axis, or could they have been to the left and still be having an imaginary component? Well, that's what D is. And D says we can apply the final value theorem to this. Because where are these values of S that cause this to vanish? This is written in a convenient factored form so that you know your poles, they're complex, and it's at -1 plus and minus J1. You know the real part is the 1 minus 1 inside the S plus 1 squared, and the imaginary component is that constant outside the parentheses, and it's squared, so that's a 1. The poles here are at -1 plus and minus J1. Those are in the left half plane. Those are going to be exponentially damped sines and cosines. How fast are they shaking? 5 radians per second? No. They're shaking based on how far they are from the horizontal real axis, how far away they are. They're up by 1. They have an imaginary component of 1. That's what governs their shaking. How fast are they exponentially decaying? That's determined by how far they are located into the left half plane. Here, maybe that's a poor example because they're the same number, but they're over into the left half plane a distance of -1. They have an e to the minus t exponential decay. When will you no longer see them? 5 tau. That's the default answer. What's tau? 1 over alpha or sigma. I guess my other class I'm using sigma, but here I'm using alpha, aren't I, for the real part. It's 1 over their distance into the left half plane, which is 1. Tau, the time constant, is 1. 5 of those is 5 seconds. You would only have to wait 5 seconds, and then it would be done shaking if it was initialized and you allowed it to now move based on those initial conditions. That's D. And you can apply the final value theorem to that. What is the final value for x sub d of t, little x sub d of t? What's the final value of that waveform? Can you apply the final value theorem? You said yes. Now I'm asking you to apply the final value theorem. You're now looking at the limit as s goes to 0 of s times capital X sub d of s. Now so the final value theorem is more helpful when you have a bunch of these connected. You don't have to inverse Laplace transform. You can just apply the theorem. That's the point. But you do have to know where all of those poles are located. And if they're all in the left half plane, you can apply the final value theorem. In this case, it's 0. These are exponentially decayed sines and cosines. They're going to go to 0. Your final value is, in fact, 0 for little x sub d of t. E. Does it have a final, or can you apply the final value theorem? I guess this should have been a D prime, shouldn't it? 1, you guys are beating me to the answers. 2, oh, you're practicing? Okay. 3. Thumbs should be up. This one does have. Why is this final value theorem? Why can the final value theorem be applied to this transform? You can have one s in the original x, can't you? Because it will get eliminated by the s times capital X sub e, and that one's okay. This one will have or allow for the application of the final value theorem. If you apply the final value theorem to this, what do you have? What is the, if you now apply the final value theorem to capital X sub e, what are you going to have? 5. You multiply capital X sub e by s, you have 5s in the numerator. Downstairs, you have an s times this bracketed expression. The bracketed expression is well behaved. You set s equal to 0, it goes to 2. This s out in front of the bracket cancels the s upstairs, and then you have a limit as s goes to 0 of 5. Capital X sub f of s, does it have, or can you apply the final value theorem to f? And that one is a little bit different than D. Question? Don't give away the answer. Question? Oh, you're back on E? Oh, thank you. So it is 5 halves. Thank you. Because I said the denominator was 2. That didn't disappear. Thank you. So, yes, it was 5, and then there was a horizontal line and a 2 down below. Yeah, you didn't see all that extra that I was demonstrating. I had a V8, but it was 5 divided by 2. Yes. Yes, the U2 are going to say, what did he just pull, right? Yeah. Yeah. So it's 5 over 2 for the answer. That's why I was getting a lot of weird looks before, as S goes to 0 on E. Now we're ready for F. That gave you some time to think about F. I think that was your plant, right? So that everybody else could have time to think. All right. 1, 2, 3. So I'm seeing mostly thumbs up, which I should be. This is a yes. Why is it a yes? You only focus on the poles in looking at the application of the final value theorem. Okay? And in this case, the poles are at -1 plus and minus j, and they're in the left half plane. What is capital X, what is little x sub f of t if capital X sub f of s is that? What do you see in the time domain, or what are you seeing now in your mind when you think about that transform, that frequency domain quantity? Maybe that's in the living room. You go into the kitchen and you say, what's it look like in the time domain? What is little x sub f of t if you see it as capital X sub f in the living room? Can you see the poles? Where are your poles? They're at -1 plus and minus j, aren't they? They're complex. When you have complex poles, what do you immediately start thinking if you have complex components to these poles? You have some kind of shaking, sines and cosines. Whether it's exponentially damped or exponentially increasing depends on whether those poles are in the left half plane or the right half plane, respectively. But you're going to have some shaking. Let's now figure out how to find the shaking parts, the sines and the cosines. You could now write x sub f of s as you go, oh, Tharp said it's a sine and a cosine. Well, what's the transform pair of a cosine looks like? What does it look like, and what does the transform pair of a sine look like in the frequency domain? The numerators differ. So now I'm not using complex arithmetic, or I'm not factoring those into their complex components, am I? I'm actually leaving them as real coefficients in the denominator. And I now want to find that denominator structure in my transform table. And I see immediately, because of the way this is written, that I have poles at -1 plus and minus j1. But I'm going to say the first one is going to be my shaking of the cosine. And what's in the numerator? What's the numerator structure if it's a cosine? It's going to be an s plus 1 structure, and I don't know yet how much of that I have, so I'm going to say there's a of that. And I have to find out what a is. The sine piece, which is exponentially damped sine, it has an omega in its numerator, and the omega in this case, maybe this is a bad example because I have ones all over the place, but the omega is 1. That's the imaginary component of those poles. I don't know how much of that I have yet, so I say I have b of that. I have a e to the minus t cosine t plus b e to the minus t sine t. So if I just ask you for the structure, you could say, oh, the structure for x sub f of s, I don't even have to evaluate ab. Why did I get this calculator? You don't need a calculator to do this if I just ask for structure. Now this is just a e to the minus t cosine t plus b e to the minus t sine of t. But I can fairly quickly, in this case, find a and b. They're both over the same denominator. My denominator is common. Let me just distribute the a's and the b's throughout. I have as plus a, and I have a b over there. And I know that that numerator needs to equal the numerator that I started with, which is 4s plus 7. I now know then that 4s plus 7 needs to equal as plus a plus b. And now I can find a and b. I have two coefficients, the constant coefficient, or the coefficient associated with s to the 0th power, and I have the linear coefficients associated with s to the 1, or the first power. S to the 1, if I equate those coefficients, on the left I have 4, and on the right I have a. Wow, I was expecting I might have two equations in two unknowns. I lucked out. One of those equations just has an a in it, and I immediately know the a. In general, you might end up with two equations in two unknowns, and you'll have to solve those coupled equations. Here, s to the 0 now says 7 is a plus b, but you already know that a is 4, and so now this tells me that b must be 3. Or if I now go back and rewrite that, I now know that I have 4 s plus 1 over s plus 1 squared plus 1 squared plus 3 times 1 s plus 1 squared plus 1 squared. And I can immediately then write down the time domain expression. I have 4 that scales this exponentially damped cosine piece, where the 1 here is the 1 there, this 1 is there, and this 4 gives me the weighting. That's where all those pieces and parts come into play. And the fact that it's a cosine is because of that numerator structure. I had an S. In this case, it was a damped S, so it was S plus 1. The other piece is now 3 e to the minus t sine of t, and these are true for t greater than or equal to 0. The 3 is the weighting. The minus 1 in the exponent is right there, and the 1 in the frequency is coming from there. Questions on that? If I now gave you on a test and said, let's say this is now y of s, what's the structure of y of t? Can you write that down? Can you write an expression for the structure of y of t given this transform expression for capital Y of s? And I hope if you don't see it now, you will see it by the exam, because you just want to it just roll right out of your brain onto your paper, or down your arm, down on your pen and onto your paper. This is now some magnitude, let's say a, e to the, what's my decay? Or is it a decay or is it a growing exponential? It's a decay because I have the s plus alpha. This is now alpha t cosine of beta t plus a b e to the minus alpha t sine beta t. I want that to just be immediate. When you see these complex poles underneath something, you now can say, oh, they're at minus alpha plus and minus j beta. I know how it's shaking. It's shaking at beta, and I know how it's decaying. It's decaying with this e to the minus alpha t. Questions on that? Let's do some initial value theorems. Suppose in the first example, example 1, we have capital X of s equaling s plus 1 over s plus 2. And now I want little x, its initial value, as time is actually coming in from the right. It's coming from big values of time, and it's approaching from the right, and that's why I'm looking at this initial value at 0 plus, on the plus side of 0. Now, in the initial value theorem, really, you could just say, well, I'm going to apply it, and if I don't have a limit, then I couldn't have applied it. It was in error to apply the final value theorem. So what am I looking for now? I'm trying to find the initial value or the initial condition in the time domain based on a limiting expression in the s domain. Yes? Does that look like what we're supposed to be using? We now take s, multiply it by this capital X of s, and let s approach infinity. That's our initial value theorem. If we now put that in, we're looking at the limit as s goes to infinity of s times s plus 1 over s plus 2. And what does that equal? You can look at it as multiplying everything out, and then you have an s squared plus s upstairs, and you have an s squared plus 2s, or you can cancel some of those common powers of s if that's cleaner for you. I would probably say, oh, let me just cancel those two. And now I'm looking at s plus 1 over s plus 2 as s goes to infinity. Do you see that s's upstairs and s downstairs dominate the constants, and now I'm going infinity over infinity at the same rate? Yes? Okay, those questions I like. You answer them yourself, or you end up not asking them somehow. But those I can answer. Did everyone get that question? I didn't. But do we see what I'm trying to do here? Now as s goes to infinity, we have infinity over infinity, and the answer is 1. In that case. So it could be applied. We had a limit. The initial value of that time domain signal for little x of 0 plus is 1. That's where we started. What about a second example? Let's say it's y of s. And this is now s over s squared plus 4. Do you see what this is in the kitchen? If you pick this up, if you saw this in the living room, we're in the frequency domain, and then you carry it, there's some magic that happens when you carry it. You're staying on this row in a transform table, and what happens when you get to the kitchen? This now comes a time domain waveform, and what is this in the time domain? What is this transform pair? What's y of t in the time domain? It's cosine because you have s in the numerator. So we're good on the cosine. What's the amplitude of that cosine? 1. What's the frequency? It's now, you really are thinking this is now s over s squared plus, plus something squared to give me 4. The frequency is 2. The frequency is the square root of that constant, which is 2. And this is now, you could write it, we're doing the one-sided Laplace transform, so this is now only on at time 0 and beyond. Or that's the kitchen version of what capital Y of S is. Does that have a value at t equals 0? So we should get the same result. We now have it in the time domain. We evaluate this at t equal to 0. That's what? It's 1. So let's see if the initial value theorem provides us with that same result. So y of 0 plus is now the limit as s goes to infinity of s capital Y of s. Or this is now the limit as s goes to infinity of s squared over s squared plus 4. S squared plus 4 downstairs, S squared as S gets big is dominating the 4. So that goes to infinity at the same rate as the numerator, and we have infinity over infinity again. We're approaching infinity at the same rate. This is 1, and that's consistent with what we saw in the kitchen. And we didn't really have to go into the kitchen. We could have just used the initial value theorem, found the limit, and said, oh, this is where you start if that's all you need. These theorems really tell us limiting scenarios without doing any inverse Laplace transforming. We're kind of inverse Laplace transforming to check our work, but you wouldn't have to. The whole point of these is to get information without inverse Laplace by just looking at the frequency domain expression. Example 3. Now we're up to z. So let's say z of s is equal to s squared over s squared plus 4. So let's apply the initial value theorem. We say, oh, this is z of 0 plus is equal to the limit as s goes to infinity of s z of s. Well, that's now the limit as s goes to infinity of s cubed over s squared plus 4. Ouch. What's this? This is going off to infinity. The limit doesn't exist, so we can't apply the initial value theorem. Does everybody see that this doesn't go to a limit? So this equals, let's say, does not exist. It's going unbounded. Now, could we see that from if now I ask you to find little z of t? Can you find little z of t? The initial value theorem couldn't be applied, so here we can say can't apply the IVT. If you're texting this tonight, you can just say IVT. Everybody will know what that means. Or if you're doing the final value theorem, it's FVT. So we couldn't apply the initial value theorem. What happens to z of t? Or how would you find little z of t? And what's the very first thing that you want to focus on if you're now inverse? I wanted to say z transforming. That's the other class. We're inverse Laplace transforming, but that z is throwing me. So it's capital Z of s. We need to make sure that that transform is strictly proper. Is it? No. The numerator is the same order as the denominator, and how do we rectify that or remedy that? We need long division. So now we can say, oh, with z of s, we now take s squared plus 4 and divide that into s squared. Doing that, we can say, oh, that goes in one time. We have s squared plus 4. We can subtract that, and we have minus 4. Is the order of that remainder strictly less than the order of our divisor? Yes. 0 is less than 2, so we can stop. And now we could say that z of s we could rewrite as 1 minus 4 over s squared plus 4. Now can you take that into the time domain? What's the first pair? What's the inverse Laplace transform of 1? That's the impulse, so there's delta of t minus S-I-G-N or S-I-N-E? I hear sine. Imaginary. So you found the roots, correct? And where are your poles? Plus and minus J2, aren't they? So now we know we're shaking at 2. And since there's no S in the numerator, we have a sign. And we have then how much of a sign? 4. What's the sign look like? If we just looked at this, now you're saying this is S squared plus 2 squared. What goes up here? 2. So now we know that this is supposed to be 4, which says that we now have 2 sine of 2t. What happens at t equals 0 plus? What's happening at the origin or at time t equals 0? It's an impulse, isn't it? So it has an unbounded magnitude. There's no initial value. And that's consistent with us not being able to apply the initial value theorem. Questions on final value theorem, initial value theorem? We had some shaking going on, causing some transient. What was the settling time? Not very long, was it? See how you can apply all this theory that you're learning? We've already done this, but let's just make sure we're clear on it. Suppose somebody gives you, say you're given capital F of S is equal to 5s plus 2 over, well, let me do it this way. Suppose it's given as s squared plus 4s plus 13. That's what you might see on the exam. Which means if you don't have an 89 or an Inspire, you need to know the quadratic formula. The quadratic, yeah, the what? What are the roots of the denominator? And when you're looking at this, you're usually focused on the denominator to see what kind of structure you're going to have. Where are these roots? You could complete the square. You could say, well, if this was imaginary, if these were complex roots, then I would have something that when I squared it, I would get 4s. And s plus 2 quantity squared would give me the 4s that I have in the original denominator. Now is 4 less than what's left, or less than the constant, and it is. So now I can add another little piece, and I'm adding now the square of the imaginary component. Or I can now say if I now added in 9 to that, I would have my original denominator. Where this, now I'm writing my original denominator as s plus 2 squared plus 3 squared. Or if I did the quadratic formula, I would see that I had poles consistent with what I've written now in red. My poles are now at minus 2 plus and minus j 3. Knowing that, you should immediately be able to figure out what is little f of t. especially the structure. The structure of f of t is now f of t is equal to a e to the what? Or somebody could have equivalently written down the structure and said, oh, the structure f of t is c e to the minus 2t cosine 3t plus theta. And that would be an equivalent answer. Either of those are acceptable. For now, what are A and B? Pardon? So there's capital F of S, and we want to now find A and B. So now we're looking at capital F of S is 5s plus 2 over and how could I expand that to find A and B? Now I just write my cosine form and my sine form and weight them by A and B. Or I now have A, s plus 2 over s plus 2 squared plus 3 squared plus b 2 s plus 2. There's my cosine structure. And there's the sine structure. And if I now look at the numerator of both sides, I'm just checking to make sure you guys are awake. To be or not to be? It wasn't 2, was it? It was 3. So we had to change Shakespeare on this one. It's 3b. 3b or not 3b? Is that classic Shakespeare? Yes. Thank you. Are we now on the same page of our written text? We now have 5s plus 2 is equal to as plus 2a plus 3b. We find A immediately, and then B is fairly quick to follow. And what's B? It's now minus 10 from 2, or minus 8 divided by 3. This is now minus 8 over 3. F of t is then 5 e to the minus 2t cosine 3t minus 8 over 3 e to the minus 2t sine of 3t. But now somebody says, well, mine was in terms of just a cosine. So how do we solve it for just a cosine? Now we do the complex number partial fraction expansion, and we do identify the factors as far as minus 2 plus j3 and minus 2 minus j3. Or f of s Now, where do I put my conjugate?
Right side, right. Oh, no, left side.
So here's where you need to be clear as to which one you label as the conjugate. You know these numerators are conjugates of one another, but you want to put the unconjugated numerator on top of which factor? Pardon?
The left one.
The left one. So what value of s causes this to vanish? Where is that pole? It's on. I'm now wanting quadrant. They're both on the left-hand side, but which quadrant is this pole in? It's in the bottom left, or the third quadrant. Is that the quadrant we want the pole in for the unconjugated k? All right, we're ready to take the exam if we correct our answer and say this is the one where we want our unconjugated k to be living on top of, because this one now has its pole at minus 2 plus j3. Here's the unconjugated k. There is the conjugated k. Are we clear on that? We need this is in the second quadrant. Yes? Why does that matter? That matters because of the sign of the SIGN of the angle. When we do our formula, we're going to find that when we take it into the time domain, it's going to be 2 times the magnitude of k1. That doesn't matter whether it's conjugated or not, but it's e to the minus alpha t cosine beta t plus theta. And that theta is the angle of k1. If k1 has a negative angle, then it would be plus that negative angle to make our time domain value or expression consistent with capital F of s. It's critical that we label or we keep that unconjugated k or constant above the pole in the second quadrant. And I've derived that, I think, in previous material. So look at that derivation and see if you can convince yourself why that's true. I don't want to get into that, but so you always want to put your unconjugated k on top of the factor that has the complex root in the second quadrant. That's the default. That's how you do it. Now, can we find the k? And why would you want to do complex algebra? Maybe you didn't like the common denominator approach because you had 2 equations and possibly 2 unknowns. Maybe they were coupled. In ours, it wasn't. They were kind of, one was immediate answer, and then we had the b from the a. Here, we can apply the cover-up method and find k1 immediately. What's the cover-up method allow us to do? Well, now k1 is going to be that factor that's underneath K1 times capital F of S. That factor is S plus 2 minus J3 times F of S, and then we evaluate that when S is equal to that value, which is minus 2 plus J3. And what happens when we pre-multiply or multiply this factor times capital F of S? We cancel that factor in the denominator. That denominator here is just made up of one factor and its conjugate. Or we end up with, for K1, we have the original numerator, 5s plus 2, over the factor that was not canceled, which really is the factor associated with the pole at minus 2 minus J3. If you mess up and you end up getting 0 in the denominator, you know you've set something up wrong, because then you've got infinity and you go, uh-oh, I picked the wrong factor, or I canceled the wrong factor. Here, this is now S equal to minus 2 plus J3, where you now have 5 times minus 2 plus J3 plus 2 over minus 2 plus J3 plus 2 plus J3. And if you simplify that, the denominator becomes imaginary, and you can divide that out. You end up with the rectangular form being 5 halves plus J 4/3. If you now treated that as a right triangle, you could find the hypotenuse, which is now the polar form will be 17 over 6 at an angle of 4/3 over 5 halves. And K1 now, if you found how many times 6 went into 17, it would be a little bit under 3. And this angle is now 28.07 degrees. We can now use that K1 to immediately go into the time domain, since that was our only factor, and we have 2 times the magnitude of K1, e to the minus 2t, which is the reason for writing it in polar form. Now we have what the magnitude of K1 is immediately. Cosine, we haven't changed how it's oscillating. It's still oscillating at beta equal to 3, at 3 radians per second, plus, and this is now the 28 degrees. This piece is now the angle of K1, and this is the 2.833, or 2 times that if you wanted to multiply it out. Now you have an amplitude of 5.67 e to the minus 2t, cosine of 3t plus 28 degrees. That's now one exponentially damped cosine that has a phase shift. And if you needed to numerically evaluate that, you would need to make sure, because this first term in the argument, this 3t, 3 is in units of radians per second, t is in seconds, that's going to be radians plus degrees. You need to make sure you convert one to the other before you add them. Yes? Where did the 2 come from? The 2 actually comes from the Euler evaluation, so it's 2 cosine omega t. We actually were looking at e to the j something plus e to the minus j something. So that 2 comes from converting it in from the frequency to the time domain. That's where so this is the standard form. If you now know K1 as a complex number, you say 2 times its magnitude, its decay, exponential decay, cosine of 3t plus its angle. That's the way, and I believe that's derived in some part of the material provided in D2L. These F's are actually equivalent. This F is the same as that F. And you need to get comfortable understanding that, oh, if I have a sine and cosine shaking at the same amount with the same exponential decay, I could rewrite that equivalently as just a cosine with a phase shift. And the amplitude's been different. And I'm expecting now, why are they equivalent? We can show this several different ways. Suppose we now thought of f of t to be r e to the minus sigma t. Now I'm going back to another notation, omega t plus theta. Suppose that's our exponentially damped cosine with a phase shift. This is really just cosine of the sum of two angles. And we have a trig identity that we can use to rewrite that or to expand that into a cosine and a sine. Or this is now r e to the minus sigma t cosine omega t cosine of theta minus sine omega t sine of theta. I'm just applying a trig identity, which is the cosine of two angles. And what happens? Well, that angle is just a number, and you take the cosine of that angle, that's a number. You take the sine of that angle, that's a number. You now just have weighted versions of cosines and sines. If we push that through a little bit, suppose I factor out the e to the minus sigma t, the exponential decay, that's common to both, and let me push the r through in each of these sines and cosine terms. Or I now can say that I have r cosine theta cosine omega t minus r sine theta sine omega t. And if I simply call this an alpha bar and this a beta bar, do you see that I now have an e to the minus sigma t alpha bar cosine omega t plus beta bar sine omega t, where I've simply used the relationship that alpha bar is r cosine of theta and beta bar is minus r sine theta. And now we could relate the alphas and the betas. Suppose I square alpha and add it to the square of beta. If I take alpha bar squared plus beta bar squared, I now have r squared cosine squared theta plus r squared sine squared theta. We can factor out the common r squared, and we have cosine squared theta plus sine squared theta. There's another trig identity, which is 1. And so now we can find a relationship for r in terms of alpha and beta, alpha bar and beta bar. We can now say that, oh, if you now have it written in this form, I can now find the magnitude of a cosine by the Pythagorean theorem. This is now just the hypotenuse of a right triangle. R is now the square root of alpha bar squared plus beta bar squared. And if you get clever and say, oh, well, tangent of theta is sine theta over cosine theta, and I can do that by dividing a little bit, my r's will cancel, and now I can have a relationship for another relationship for alpha bar and beta bar. Or suppose I take beta bar and compare and take the ratio of that with alpha bar. I have minus r sine theta over r cosine theta. Or if I multiplied the numerators by minus 1, I could say that theta is now the inverse tangent of minus beta bar over alpha bar. And now we have theta. That's the phase shift in the cosine expression. And I'll let you look at the example. I want to quickly show you that you could actually do this graphically instead of just, well, I don't know, these formulas, I'm just going to apply them. No, you can actually kind of sketch this and see it for you in terms of what is happening. Suppose we said, or we could combine sines and cosines graphically. In this case, here's my chart, and I'm going to say this horizontal on the right side is the positive cosine direction, which is really the alpha bar or associated with the alpha bar. And down below is actually the positive sine direction, and that's because of that negative sign that came in to play when we found the sum, or we used the trig identity for cosine of a plus b. In our case, what was the component in the cosine of our two expressions? Now I'm looking at this and I say, what was the weighting of my cosine piece? That was 5. What was my weighting on the sine piece? Well, that was a minus 8/3. Remember those numbers. And now I'm going to put that in the chart or in the graph. I need to go over to the right 5. That was in the cosine direction. That was the coefficient that weighted the cosine. In the sine direction, the positive is down below, so I want to go up because it was a negative 8/3, which is 2 2/3, and it was in the negative direction, so now I'm right about there. That was the 8/3. And I can now draw my rectangle and finish with my hypotenuse. There's R. I could now I could see this graphically, and now I can find the magnitude of that hypotenuse. That's 5 squared plus 8/3 squared, square rooted. That's R. And what's that angle? Well, that's now the angle that has an inverse tangent of 8/3 over 5. And that will give me the 28 degrees that I needed. And that's how you can now compare or combine sines and cosines graphically. Another way that you could check this is you could say, If I now had sine of x, how is that related to cosine? Is that the relationship? So now if you looked at cosine of x minus 90, again if you applied this, it's cosine of x cosine of 90 plus sine x sine of 90 degrees. What's this? 0. What's this? 1. So there is sine of x. So if you now had sine of x, that's the same as looking at x minus 90 degrees in this particular picture in terms of the cosine piece. And we're out of time, aren't we? So that's enough, I think, to get you ready for exam number 2. And I'll see you, if I don't see you in just a little bit, I will definitely see you Thursday.